Welcome everyone, and thank you for joining us today. The webinar will begin shortly. The title of today's webinar is Solar Heating for Industrial Processes. This is a webinar of the IEA Solar Heating and Cooling Program's Solar Academy, hosted by the International Solar Energy Society, ISIS. We are looking forward to all of your participation and questions in the Q&A session later. My name is Joanna Costello, and I'm going to be taking you through a short introduction, and I'll talk to you again at the end of this webinar. Before we begin with the webinar presentations, I would like to inform you about what ISIS is and stands for. The International Solar Energy Society is a non-profit UN-accredited membership NGO. The ISIS vision is to achieve 100% renewable energy for all, used efficiently and wisely. We represent a diverse membership of academics, researchers, energy practitioners, consultants, students, businesses and advocates. ISIS works together with like-minded organizations from countries around the world to advance the renewable energy transformation. By becoming a member of ISIS, you are supporting the 100% renewable energy movement. We understand that sometimes the time of these webinars may not suit people in many parts of the world. While we try to alternate webinar times to suit as many time zones as possible, it is not always possible. Therefore, we will post the recording of this webinar on our website, ises.org, on the ISIS YouTube channel, and on the IEA SHC Solar Academy website and the IEA SHC Solar Academy YouTube channel. All the links are available on the website. You are welcome and encouraged to ask questions at any time throughout this webinar. To ask a question, select the questions pane on your screen and type in your question. Please specify who your question is directed to. Questions will be addressed after all the presentations in a Q&A session. We would also like to encourage you to use the ISIS discussion forum on LinkedIn to continue the Q&A and the discussion even after the webinar has ended. A special thank you to the International Energy Agency's Solar Heating and Cooling Program IEA SHC Solar Academy for the organization of this webinar. I will pass over to the webinar moderator, Werner Weiss, who is an executive committee member of the IEA SHC program. Werner will give you further information about the program and take you through the webinar agenda. Wishing you all an enjoyable webinar, and I now hand over to you, Werner.
Okay, thank you, Joanna. As mentioned already by Joanna, I'm the moderator of this webinar on solar heating for industrial processes. This webinar today is the second of a series of webinars organized by the IEA SHC program Solar Academy and hosted, as it was mentioned already by Joanna, by the International Solar Energy Society. I want to give you just show you a few slides on the IEA Solar Heating and Cooling Program that you get a little bit of a background. Currently, we have 21 countries as members and another 47 additional as sponsors. So we work worldwide in research and development in different so-called tasks, which are projects, basically on solar heating and cooling topics. So we are really represented worldwide, and why a Solar Academy? We discussed it several times, so how to inform people about our research results, and we have 4 ways to do it. One are the webinars, what we are doing today. Another possibility is what we are currently doing is we produce videos highlighting our work at different solar thermal issues. So there's a first video package of 11 videos is available, which we made at the Green Expo held in November 2016 in Doha. Another option is we organize national days. We usually through our executive committee meetings. So if we are in the country, then we organize national days and distribute our results. And last but not least, we offer on-site training in different countries. So if you want to know more about it, you can find more information on our website. And of course, you can follow us also on social media. Last but not least, we would be happy to find all of you at our joint conference which we're organizing in November this year. So it's the Solar World Congress organized by ICES, and on the other hand, the SHC 2017 conference organized by the SHC. So it's a joint conference taking place from 29th of October to the 2nd of November in Abu Dhabi. So maybe we see each other there. So that was a little bit on a background on the IEA Solar Heating and Cooling Program. Coming to the topic of today, as you might know, solar heat for industrial processes is a research topic now for several years already. And when the last task we were working on, the solar heat integration for industrial processes, was launched in 2012, there were about 120 of these so-called SHIP systems, so solar heat for industrial processes, with about 88 megawatt installed or at least recorded. And since 2012, we have a recorded number of more than 500 systems worldwide, in the range of 291 megawatt installed capacity. So this was a tripling in a relatively short time. And this shows there is a huge interest in this topic. We have three panelist speakers today. One is Christoph Brunner, which is a colleague of mine from IEA in Austria. We have Pedro Horta from Fraunhofer Institute for Solar Energy Systems in Germany. And last but not least, Bärbel Epp. She's from Solrico, from Germany. She's a journalist, and she will give us at the third presentation information on investment opportunities in solar heat for industry. Coming straight to Christoph. Christoph studied process engineering at Graz University of Technology. He worked as a department manager at Joanneum Research in Graz in Austria and joined our institute, IEA in 2010, and built up there the Department of Industrial Processes and Energy Systems. So he's really an expert in this field, and he is also running several EU projects on this topic. I just want to hand over to Christoph and ask him for his presentation.
Okay, thank you very much, Werner, for this introduction. Yeah, welcome to all of you to my presentation on the global fuel on solar heat for industrial processes. I want to give you an overview from planning to realization and give you some examples. In general, industrial heat has a very important role in the global economy. As you can see here on this first slide, the demand of solar thermal energy for industry depends on the development of the industrial companies from one country to the other country. We can see, for example, in regions like Latin America, Middle East or Asia, that here we have quite a high share of the total energy demand, which is related to the industry. And for example, in Europe or in Africa, this share is a little bit smaller. But in general, it is well known that industry takes a quite huge amount of energy what is consumed worldwide. If we have now a more closer look on an overall look of all continents, you can see approximately 1/3 of the total energy consumption is allocated to the industry, and different to maybe the public awareness that people are thinking the most energy is consumed on electrical from electrical sources. You can see here that 74% of this 32% of the total energy demand for industry is thermal energy. And this is split into 45% for coal, 30% for natural gas, then 50% for oil, and then approximately 10% for renewable energy. If we have now a look on this 74% for heat, you can see this is approximately 85 exajoule in total, and you can see here a share that 30% allocated to low temperature heat, so below 150 degrees, 22 is between 150 and 400 degrees, and 48% it's everything above 400 degrees for this demand, thermal demand in the industry. You will ask maybe, why is it so important to know these different temperatures? This is linked on the one hand, of course, to the different collector technologies, and of course then to the efficiency related to these different collector technologies. On my next slides, you can see here the different industry sectors, starting, for example, with chemical industry, food and beverage industry, machinery industry, mining industry, textile industry, wood industry, and their processes which are linked to certain temperature levels. So we have quite a lot of processes which are running below 150 degrees, like boiling, drying, pasteurization, sterilization, cleaning. In the mining industry, for example, copper, electrolyting, refinery, mineral drying processes, or in the textile industry, washing, bleaching processes, in the wood industry, pickling, cooking, steaming processes. These are processes below 150 degrees. And then we have for these industry sectors also some processes which are running in this temperature range between 150 and 400 degrees. And then all these industries like the steel industry, they are linked then to processes above 400 degrees. And here below you see different collector technologies. So mainly you can separate the collector technologies in non-concentrating technologies and concentrating technologies. But you will hear then from Pedro Horta, who will follow my presentation, more about these different collector technologies. So industry sectors, different temperature levels, different processes, and this is, let's say, this was the basic for our considerations how to implement solar thermal for different industry sectors. But what are the challenges to implement renewable energy for the industry? What is clear that solar thermal will not be the only energy source which is linked to supply of the energy to industry. There will be always a hybrid system. So this means solar technologies will be applied in combination with, for example, biomass or biogas boilers or geothermal technology or heat pumps. The second very important point is we have to implement the different technologies based under exegetic considerations. What does it mean? As you saw in the earlier slides, temperature is a crucial point, and you have to apply this technology which fits best to the certain temperatures for the processes where the energy is needed. Then matching of variable solar resources with load profiles, this is quite a challenge. So it means on the one hand our solar energy yield is has a certain load profile. So it starts in the morning, at noon you have the highest yield, in the evening it goes back, or they will reduce this yield, and also your processes will have a certain load profile, and this you have to match and find out the best solutions. Energy management, energy efficiency, it's a crucial point. This has to be in combination with the integration of renewable energy in general. So this is a very important part what has to be done first before you want to implement solar thermal. And what the role of the industry in the future can be seen as a so-called prosumer. This means industry will interact with the environment. They will take the energy from networks, also from district networks, for example, but also will bring in the energy, for example, waste heat into this district heating networks. So these are the main challenge, and we face this challenge as in our IEA task, which recently has been finished. Werner Weiss already spoke about it. This was this IEA Task 49 on solar process heat for production advanced application. It was a joint task, solar heating and cooling program of the IEA and the solar basis program. It was a pleasure for me to coordinate this IEA task. It started in February 2012. The duration was about 4 years. 15 different countries participated. We had 21 research institutes, 13 universities and 22 companies which participated to this IEA task. And we considered all industrial processes up to 400 degrees. So as what you saw in the earlier slide, these processes at low temperature and medium temperature, they were addressed in this IEA task. We had a look on different heat carrier medias like air, water and low pressure steam, and we considered all different types of solar thermal collectors. As a further information, you can click on this link on task 49, this website, and here you find also all different informations, reports, what I will present now in my presentation. If you have an overall look on an overall concept for solar process systems, we can see different areas. So on the one hand, we have the collector loop or the collector field with the collector technology. Then we have the charging part with a heat exchanger. Then we can have a storage system which is charged and discharged. Then we have the integration point into my process site, into my production site, and then we have the conventional process heat system. So this has been always into exchange with my solar process heat part. So you see here these different sectors, but it's not absolutely necessary that in an installed system you have all these different sectors. It could be that some of the sector can be replaced or can be exchanged. And this task was now built up on 4 different subtasks, so 4 different fields. On the one hand, on process heat collectors, which was coordinated by Pedro Horta. Then on the process side, based on process optimization, process integration, and process intensification, this was coordinated by my colleague Bettina Muster. And then the overall part, this was about case studies, integration equipment, and dissemination, which was coordinated by Werner Platzer, also from Fraunhofer ISE. And now I want to go into these 3 areas, these 3 thematic areas, and give you some examples of the output of the task 49. So first on the process heat collectors, and together with the European project STAGE-STE, a general database for process heat collectors has been developed, and here you can find different informations on type of the collectors, on the manufacturers, collector model, of the performance of the collectors, of course, which is very important, if it's certified or not, where you can apply this collector best, and also stagnation protections. These are this information what you can get out of this database, and with this information it will get much easier to select the right collector type for installers, for planners, etc. Another output was a report, a report with very practical solutions on overheating prevention and stagnation handling. The main challenge for large collector fields in solar process heat can be these overheating and stagnation problems. What does it mean? The efficiency, if you overheat a system or a solar system goes into stagnations, then the efficiency goes to zero and you don't get any energy out of this system anymore. And this can happen when, for example, the production process on the company side has a problem. So there's an unforeseen stop of the production, for example. They need no energy anymore, and so the whole system can go into this overheating or the stagnation part. In this report, you get really practical solutions, measurements, measures for solar process heat applications with non-concentrating collectors and with concentrating collectors. You get different solutions, how you create and how you design such stagnation solutions in order to avoid this stagnation problem. Coming to the process side, here we have these different approaches that we say, okay, we want to have a very efficient system on our production process side. This means that we want to reduce our energy consumption first, and after this optimization of our production process, after maybe reducing the temperature levels of our processes, then go in and integrate the solar thermal system. And here it was really important or crucial to know about the processes, to know about the whole industry where you want to integrate solar thermal system, to have here a very good basic and a very good knowledge about this. In this field where we worked here, we developed different tools, or these following tools and programs to reduce these energy consumptions. For example, a software tool on a methodology and for creating heat exchanger networks for minimizing the energy heat demand. We also created tools to identify the right technology for different processes, and also to identify maybe emerging technologies which could be applied in the future. And what is also very crucial, to identify or to create a methodology and a tool to identify the best integration point for solar thermal systems in the industry. So this on the one hand this part, and then we also developed an integration guideline how to integrate solar process heat into practical design rules and for planners and installers. Here we developed integration concepts, but Pedro will speak then later more about this. And we also developed an database, an online database, the link you will find here. And on this online database, you get practical information about industrial processes, integration concepts, temperature levels, where you find these different processes in the total production schemes. So very practical information for people who are not so familiar with industry and industrial processes. Coming now to this field of case studies, integration equipment and dissemination, I picked out, I think, a very important output here. This is an online database of realized or the existing ship plants. At the moment, we have registered about 253 plants worldwide with a total collector area of more than 190,000 square meters. And you can, if you go to this link ship-plants.info, you find here possibilities to search for installations selected by countries, by applications, by solar companies, by collector technologies, by year of installations, by industry sectors, etc. So I think this is quite interesting website, and now I want to give you some statistics out of this website. For example, the installation of different collector technologies. So you can see here on the one hand this dark green or blue column, it's the cross area installed. The light green column is the thermal power, and here this is the number of installations, and here now the statistics about the different collector technologies. Most of the installations are using flat plate collectors. As you can see here, it's about 98 megawatts, which are for non-concentrating systems installed, so flat plate collectors and vacuum tube collectors, and about 13 megawatts the concentrating collector technologies like Fresnel collector or parabolic trough collector. Have a look on the different installations on different industry subsectors. You can see here that most of the installations are in the food and beverage industry, like here and here. If you combine this, these are the biggest number. But from the cross area or thermal power, mining industry and textile industry are following and have more or less at the same range. So there's also quite a high collector field and thermal power installed in these two different subsectors. Here you find here a graph where you see the installation in different areas worldwide. So the green dots are installations in Europe, the red one in Asia, the blue one in Africa, and the pink one in America. And as you can see here, most of the installations from the number are in Europe. From the cross area and thermal power, most of the installations are in America. And especially here, as you can see here, these dots, this is reduced by the factor 5 because this shows the biggest installation in Chile, which is installation for a copper mine. So coming now already to some pictures that you see. Okay, all these installations are real. You find these pictures also on the website on this database I showed you. Just going from here left on the first line, this is an installation in a brewery in Austria, which was done in a European project, and especially there was some innovative technology used on the process side in order to make it possible to integrate this 1,500 square meter in the brewery. Then we have an installation in Switzerland, which is for a dairy industry, where we use this concentrating collector technology for producing steam. Then here is this installation in Chile, this biggest installation at the moment for 39,000 square meter flatbed collectors for a copper mine production. Then here, this installation, this is installation in China for a textile manufacturer, about 9,000 square meter evacuated tube collectors. Here in the middle, you find an installation which is running several years already. These are air collectors, and they are supplying this hot air to a coffee drying production. Then we have one installation in Italy with Fresnel collectors. This is a 995 square meter collector field for a dairy industry again. Then we have an installation in Mexico, which is for food production, about 3,700 square meter. unglazed collectors, so quite interesting also. They are really producing energy at very low temperature. Then we have one installation in China on the textile industry, 13,000 square meters, flatbed collectors, and again concentrating technology in China for chemical industry, chemical products, steam generation, directly steam generation, and feed in this steam in the process itself. Yeah, coming to the end of my presentation, I want to give you an outlook. We are planning at the moment a follow-up of this task 49. This task has the focus on low temperature solar radiation technology, which should be implemented in fluid separation technologies and water treatment technologies for industrial applications and sewage plants. This is the focus of this following up task. These are these four main fields. So we want to have a look on thermal driven low temperature water separation technologies. We want to have a low temperature look on low temperature solar collectors as a reactor itself. We want to address water detoxification and disinfection systems, and we also want to again summarize them with system integrations and best practice examples. And I really, for those institutions which think they can contribute to these different fields of applications, I really want to invite everyone to get in contact with me, and maybe we can meet then in one of the coming up task definition phases. Good, thank you very much for your attention.
Thank you, Christoph, for your comprehensive presentation. I directly want to go to the next presentation, which is given by Pedro Horta. I mentioned it already. He will give us an overview on the available technologies, design procedures, and upcoming innovations. Pedro graduated from the Technical University of Lisbon. He has a degree in mechanical engineering and a PhD in technological physics. And he's working, as I mentioned already before, at Fraunhofer ISE, and he is the head of the group of thermal industrial processes and systems. He was also involved in this task 49. He was leader of subtask A. It was mentioned already by Christoph before. And I think what's also important, he is at the moment coordinator of the H2020 project. It's a European project called INSHIP, Integrating National Research Agendas on Solar Heat for Industrial Processes. And I think you can see here with this project, Integrating National Research Agendas, it's already on a broad scale of interest, because there are several countries who are working on this and have research programs on it. So I'm really looking forward to hearing from Pedro what he can tell us about available technologies, design procedures, and upcoming innovations. Pedro, the floor is yours.
Werner, thank you so much for the nice introduction. Good afternoon to you all. Thank you so much for attending the webinar. So I'm going to provide you an overview on what are the available technologies, design procedures, and what are the upcoming innovations regarding new research topics, and what are the challenges these technologies and applications are facing. So as Christoph Brunner has already presented before, what we can see from the statistics is that the use of heat in industry is predominant. And if we look into temperature levels in different industrial sectors, what we can see is that roughly half of these heat requirements are in both the low or medium temperature range, and it's important to refer that because these are the temperature ranges for which we have available technologies today. And also then there is a distinction between the so-called energy intensive sectors like iron and steel, like chemical, petrochemical, and so forth, which have predominantly high temperature processes, and then the non-energy intensive sectors such as food and beverage, textile, machinery, and so forth, which are pretty much in line with what Christoph Brunner presented earlier. So coming to the technologies and starting from a basic definition on how to assess the efficiency of solar collectors. A very basic concept, those who are not so well aware of the technology, is that of course the efficiency of a solar collector depends on its operating temperature. And what we know is that these that thermal losses, they are proportional to the difference in temperature between the ambient and the temperature at the collector. So this means that as we go higher and higher in operating temperature, we will have higher thermal losses. So as for us to reduce those thermal losses, there are different strategies which depend on the selection of different materials, on the use of glazing covers, or on the use of concentrating optics, which then will represent from one side lower thermal losses. So that means that as we go into higher temperatures, this curve will not be so steep, so we will have lower thermal losses. But of course, at the same time, if we are using glazing, if we are using mirrors to direct the radiation to some specific targets, then of course we are introducing some optical losses. So what we see between different technologies is always a gain between optical and thermal losses. And pretty much what we need to understand is at which temperature level are we trying to work, and then upon this temperature level, what's the most suitable technology which delivers a higher efficiency. So we can divide these technologies into tracking collectors. Tracking collectors use concentrating optics. We are going to look some examples, and stationary collectors, which do not have concentration, so they are prone to higher optical efficiency, but also higher thermal losses. That's what we can see in here. So this would be a range of efficiencies for such collectors. And tracking collectors or concentrating collectors, normally they present a lower optical efficiency, so they have some penalties on the optical side, but they present higher thermal performance, so lower thermal losses. And we would have efficiency curves more or less in this range. So looking into what are the available technologies, so stationary collectors, they present lower operation and maintenance requirements. Normally they present also lower system costs, but of course they are limited in terms of operation temperature. Normally limited to low temperature processes, meaning temperatures below 150 degrees. The two main technologies on stationary collectors are flat plate collectors, so common temperature range between 30 and 100 degrees, and then evacuated tube collectors, already with some thermal enhanced strategy, vacuum, which present common temperature ranges between 50 and 130 degrees. Then looking into tracking collectors, so tracking why? So all of these collectors, they use concentrating optics. And well, for those interested in knowing a bit more about that, I would be happy to give you some details. But basically, as we concentrate radiation with mirrors, lenses, the optical effect is to reduce the field of view of the system towards the hemisphere. So that means that if we want to see, and then here between brackets, if we want to see the sun along the day, of course these collectors have to follow the sun trajectory along the day. So that's why we call to these technologies tracking collectors. And there are three main technologies on this regard addressing solar process heat systems, and those would be parabolic troughs, linear Fresnel, and parabolic dishes. There is a fundamental difference between the two first systems. So both of them, they are so-called line focusing systems. So they direct the solar radiation into an absorber which is cylindrical, which is a pipe, as you can see here. Whereas the third technology, parabolic dish, is a so-called point focus technology, and as the name indicates, so the solar beam is directed to a point. So we have a point receiver in this case. So all of these technologies, they rely on the use of mirrors. So of course mirrors are a very important component in the design of such systems. They might rely or not on evacuated tubes as receivers in the case of line focusing systems, so also a very important component. And they can address a temperature range between 150 to 400 degrees with line focusing technologies, and I'm talking about currently available technologies, and with parabolic dishes we can go maybe a bit higher than 400 degrees. So this picture here pretty much summarizes which technologies are available for which temperature ranges and which industrial branches present heat requirements in these different temperature ranges. So this also was presented by Christoph Brunner on his presentation. So this scheme pretty much summarizes all of this information. The message is that yes, we have available technologies addressing a wide range of applications in industry and about half of the total heat demands in industry. Well, looking into how to design a solar process heat system, there's one very important first step, which is to realize what's the energy efficiency potential. Because of course, when we invest on a solar system to produce heat for an industrial process, we don't want to waste this heat, because of course any wasted heat is not going to contribute to our return on investment. So the first step is always to take some considerations into the energy efficiency potential. And on that regard, there is one tool, a pinch analysis, very well-known tool, which basically enables us to have an overview of the current processes in a given company, so the current heat supply and heat consuming processes, and draw a picture of how can we recover heat from one process to the other, and to identify basically what would be the maximum heat recovery potential in this company. So this is what we can see over here. So the heating and cooling requirements are characterized by two different curves, hot and cold composite curves. That's the name of these curves. And basically the overposition of these curves enables us to identify what's the maximum potential for heat recovery between processes and what are the effective cooling and heating requirements in the company. So this is the first step to consider then where should we act with the heat supply system, with a new heat supply system, which would be the solar system. So basically, our solar system design is going to tackle the effective heat requirements in the company, considering that energy efficiency measures are undergoing or will be taken in the near future. Then one other very important question is how are we going to integrate solar-driven heat into the plant? And of course, as Christoph already mentioned, there are different integration possibilities, and they are basically classified into supply level or process level integration. When we speak about process integration, we are talking about integrating solar heat directly in one specific process. This kind of layout has a lot of advantages. So the first of all is that we can come much closer to the process temperature. And normally, it's very often we find in industry processes which are run at rather low temperatures, but they are supplied with steam. So there is a huge difference between its supply temperature and the process temperature. So when we go on a process integration strategy, we can achieve lower temperatures on the heat supply, and we have already seen that lower temperatures mean higher efficiencies, potentially use of simpler technologies. And what we can see in this scheme is that this is the basic heat supply and consumption scheme on an industrial company. So we have a boiler supplying steam, low pressure steam, maybe to some processes, different processes running at different temperatures. We have a condensate line, and then we have a share of makeup water. So, and we can see here what would be the possible integration points for both tracking or stationary technologies. That's what we want to illustrate in this scheme. So it is important to take into consideration the effective heat requirements first, and at what temperature are we going to operate our solar system? Thus, where are we going to integrate solar heat? So there are some criteria to reach a conclusion on whether to act at supply level or process level. Very important to have in mind that normally industrial end users are very reluctant on process level integration, because of course they don't want to interact directly with their processes. So we have to have that in mind, even if it would be beneficial from the solar design side. Regarding the development of pre-feasibility or pre-feasibility studies, so the objective is to have an holistic planning approach, which starts with the pre-analysis, focusing on what are the boundary conditions for our project. This includes what's the motivation of the company, includes also whether or not there is available space to install a solar system. Then we go to analysis of process characteristics and a characterization of the existing heat distribution network. And finally, we look into possibilities on process optimization and energy efficiency measures. So only after we go through all of these questions, we are ready to start looking into how are we going to design our solar system. So there is a rather comprehensive methodology developed and provided within the framework of Task 49. You will be able to find all of this information in Task 49 publications. I have the references and links in this presentation. You can follow them afterwards. Then we have to dimension the system, to have a system simulation tool, and there are different tools available. There is a rather comprehensive description and even comparison of such tools in Task 49. I'm providing here some examples of such tools. We have simplified tools such as nomograms. Senocalc is a tool, a simplified tool provided in the framework of Solar KeyMark certification scheme for solar collectors. And then we have more sophisticated tools which enable even some dynamic simulation of these systems. Looking into the challenges these technologies face, so we have technologies challenges and competitiveness challenges. On the technology side, one very evident challenge is, of course, how to tackle higher temperature processes in energy intensive sectors, but then we have also questions regarding how to integrate solar heat at process level, how to include process intensification in this game as well. Balance of plant questions, how are we going to integrate solar steam in steam networks, how are we going to integrate the collectors in scarce space availability situations, hybridization with other energy sources, durability of these equipments in industrial environments. And then, of course, from the competitiveness side, we need to focus on technology cost reductions, how to develop financing schemes, how to cope with COP21 emission goals is also a very important topic. All of these questions are addressed in these projects I have listed here. There are other projects, even these are just examples of projects where such questions are being tackled. And finally, to mention the ETRIA on solar process heat, which has started in January this year, is being coordinated by Fraunhofer ISE and has 28 partners all over Europe. We are trying to develop coordination actions towards coordinated objectives and specific research activities, and these research activities are developed at rather low technology readiness levels. So basically we are developing new concepts and we are trying to demonstrate these concepts at least at the lab or small prototype scale. And within the topics which were defined, we look for solutions for solar integration, solar technologies for high temperature processes, and how are we going to integrate solar process heat in the overall energy system. So those are the main objectives of these research activities. You have some further detail on specific activities within different work packages here, and of course information on the project is available on the project website. We call also for the participation of external partners, as there is an infrastructure access scheme foreseen in the project. I would conclude here my presentation. Thank you so much. I'm open for your questions now.
Thank you, Pedro, for the very good presentation. In my point of view, it showed clearly that it's really a challenge to go in this field of solar heat for industrial processes. It really requires the knowledge, on the one hand, from solar thermal companies, and on the other hand, a lot of knowledge is needed concerning process engineering. To bring this together, I'm sure we are coming back to this question afterwards when we have the Q&A session. So, but in my point of view, it really showed very clearly that it's not just about solar thermal knowledge. You need also a lot of knowledge concerning process engineering.
And financing, if I may add.
And finance. Yeah, that's I just wanted to mention. That's the next presentation done by Bärbel Epp. Bärbel is Managing Director of the agency Solrico, based in Germany. And she is responsible also for the monthly newsletter at solarthermalworld.org. I guess a lot of you know it. Bärbel is for many years the voice of solar heating and cooling, not only on the solarthermalworld.org. She writes a lot of articles and is aware what's going on worldwide. Solrico published the first world map of solar process heat specialists at the beginning of 2017, so just recently. And she is also partner in the international project Solar Payback that aims at increasing the development of solar heat and industrial processes in 4 partner countries, namely India, South Africa, Brazil, and Mexico. And now maybe also we have several listeners here in the webinar from India. I saw it with the questions. Maybe you can also give a short focus on India. Bärbel, the floor is yours, and I'm looking forward to hearing your presentation now on investment opportunities in solar heat for the industry. Bärbel.
Thank you, Werner. Thank you very much for the nice introduction. Well, I think we are in a very special time at the moment, when webinars about SHIP attract more participants than webinars about PV and wind. That's what happened to ISIS recently. We have more than 500 people registered, and the last PV-oriented webinars had less than 500. So there's a great momentum for SHIP worldwide, and I will present you in the next slides some market indicators that verify this momentum. We have a strong demand increase. I think this was already mentioned by Werner before, the 500 systems which were, sorry. Do everybody see this navigation?
Yes, we can see your
Okay.
presentation.
We can hear everything. Okay. Well, so this for over 500 systems was, you know, from our latest survey, the World Map survey, November, December. This is the latest market assessment. We have, among these investors, we have found many which are very satisfied. We heard already about tanneries, that means cloth production. There's one from Vietnam here saying that our customers are interested in increasingly looking for eco-friendly suppliers. So this was his motivation to invest without subsidies in Vietnam. And we have one statement here from Mexico as an example of a body and hair production unit. And he was extremely delighted that his solar water preheating process heat system even increased his efficiency in the emulsion by 40% because it reduced production time. And this is something I want to stress very deeply from what we learned looking at case studies, that solar engineers are very good in increasing efficiencies and increasing also processes in factories. And a very famous example is this copper mine, which was mentioned before. The person you see in the bottom is Ian Nelson. He is the general manager of Pampa Elvira Solar, the operator of the plant. And the delivery contract he signed with the copper mine made him, you know, deliver temperature range in a very narrow range. And also he's operating the boilers for the copper mine and delivering heat with a certain fixed quantity, and he has to pay penalties if it doesn't work. And what happened by this contract, which he fulfilled for 3 years now, that the copper cathode quality increased and the copper mine was able to get a quality trademark on the London Metal Exchange. So I think we should keep this in mind when selling solar process heat, that we not just sell an ecological heat source, but we also sell good efficiency consultancy, and this is often of the same value to our clients. The biggest investment at the moment is from in Oman, a US $600 million investment, which is installed at the moment. They are installing the glass houses, which will have parabolic shafts included later. It's a 1 gigawatt plant, which should produce the first steam, parts of it, at the end of the year. And Katie Strubel, the marketing director of ClassPoint, who is the company from US who's building it, told us that it's in schedule and under budget, which is unusual for large-scale projects. Hopefully it's not only propaganda, but I think we should mention that against investors, this enhanced oil recovery is a big potential. There might be more projects coming up also in Kuwait. It means that solar steam is used to heat up oil in the ground or to make it more liquid, so it's easier to pump it up. A business case from Mexico, which is a very viable market at the moment, from Inventive Power. They use these parabolic draft collectors and calculated that their heat prices are factor 5 and 6 more cost effective than diesel boilers and LPG boilers. You find this case study completely on solarthermalworld.org with all figures that you need to make your point up about this calculation. It's a 15 years lifetime calculation. Well, this is the world map, which is full of 71 suppliers in turnkey solar process heat. This is the main message for you today, that we have an increasing supply chain. Among these 52 suppliers, we have 29 which are ready to offer. That means they are startups, they are enlarging their portfolio, they are interested in the sector, they want to sell, they are convinced of the potential, and 42 are already established. In this map, you see always the collector type which the company is producing, but not all of them are producing collectors, but only offering turnkeys. And you find next to the company name the number of references they did in turnkey ship and the collector area they installed. This is showing some of the results of the companies mentioned. parabolic draft of, well, let's see, of the 52 companies which produce collectors on this map, 18 produce or use parabolic drafts for their process heat, 10 flat plate, vacuum to linear, and dish is not so strong, and 29 decide to be technology neutral and just offer turnkey. Another important figure on this chart is that already 24 companies are offering supply contracts, heat supply contracts instead of hardware. Ship industry seems to be concentrated at the moment in China, Mexico, India, and Germany. This is what you can learn from these rankings. On the left-hand side, we have listed the companies by the number of turnovers they had installed in the years, only ship actually, so we cleaned their reference listers a lot by getting rid of hospitals or whatever they had in their reference listers and just left ship plants or ship projects included, and this gives the numbers which are mentioned here. And the ranking is absolutely dominated by these 4 countries. On the right-hand side, we have listed the companies with the largest installation, which is also a category, like the Pampa Elvira Solar in Chile. A professional supply chain needs partnerships, and we see that there is a great momentum in China at the moment because the potential for process heat and district heating is very strong there, and Chinese companies, collector manufacturers, are increasingly looking for strategic know-how partnerships abroad. The photo on the top is between Sunrain and Arcon Sunmark. They founded a joint venture a year ago to develop large-scale solar thermal systems in China. The photo on the bottom is Green One Tech and Haier. Haier is an appliance company from China. They just purchased 51% of the flat plate collector manufacturer Green One Tech. The objective here again, the development of large-scale collectors in China, production. And so we see that the focus is always on providing large fields, large solutions. It's big business, and big players from China are doing these kind of investments. CSP Aalborg, SoltX Technology, is also a new corporation. It's not China-Europe, but within Europe or US. It's because of developing a storage tank on salt, which is also, CSP Aalborg is also a player on our world map. So we had a professional supply chain, we have an increasing demand, and we have huge potential. So the 3 factors are together to have a strong market development. This chart here shows you where we are. The beginning is at 0.001 exajoule of solar heat contributed worldwide. REMAP, the study from IRENA, International Energy Agency, is focusing or assuming a share of 2.2 exajoule, which would be something between 800,000 and 1,300 million square meters in 2013. And I want to jump back now again to one of these charts you have seen before, which shows us that 2014, the providable energy demand, heat demand in the industry was 44 exajoule. So we are very small still, but we have a very, very big potential. And this again repeats the industries which are most suitable for it.
Bärbel, sorry to interrupt.
Yes.
Oh, now it's moving. It was stuck for a minute, but now it's moving.
Okay. So we have a momentum, but there is always a but. And the but is the vicious circle of low deployment rates. And this is very placative, showed in this chart. We have small numbers of plants. You have heard 500 worldwide is not really a big number. We have little visibility of existing systems, which makes again low awareness in the industry, which leads again to small numbers. And on the left-hand side, we have this very big bottleneck, which is triggering or really harming the suppliers at the moment. High upfront investment costs plus low energy prices brings the payback periods up and also, makes it very difficult to sell. So I think we don't have to hide, and we have to make it very clear to decision makers in all levels that the potential is big, all the momentum is there, but it needs strong support and a great effort to make this happen. And we have asked the ship suppliers for their assessment on market difficulties during our world map survey, and 54 of them mentioned difficulties with securing funds on one of them as one of the main retarding factors. 33 believe that huge efforts are needed to make solar process heat projects bankable. So the financing, which Pedro mentioned at the end of his presentation, weighs as strong as technical issues. And very important as well, 79% see heat supply contracts and ESCO models as an important means to increase deployment. But so far, as I said before, only 24 are offering it, because it's also a high risk for a small ESCO company or a solar thermal system provider to take the responsibility for a long investment. So we stress 3 ways to break this vicious circle. I think there is a great need for further communication towards policymakers, but also towards potential customers via associations on conferences. So the communication needs are incredible. We need financial supports which are intelligent. It's not in all cases subsidies, but it can be also, reducing risks by giving, heat supply guarantee for smaller investors. There are very different activities, but financial models and reducing risk is a very important issue, because this is stressed a lot by the ship suppliers. And last but not least, this whole issue of energy prices can only be solved, and IEA tells us that the energy prices will stay as low as they are for the next years. So payback times will be very difficult to reach, and only carbon taxes or renewable quotas in certain industries will break this civil circle and this respect. And India actually is showing a way. I think they have drafted a kind of renewable quota, which is now assessed by the ministry, and the industry is hardly fighting for it to get a similar rule like a PV, and maybe they can show us the way. Most of what I said is covered in these solar heat for industry brochures, which we have produced in the solar payback project, and they are available in English, Spanish, Portuguese. You can download them at the moment at sorico.com in the subsection of solar payback. And from 1st of August onwards, we will have a website, www.solar-payback.com, and we will have 3 years more to go to do a lot of communication and project development in these countries which were mentioned before: India, Mexico, Brazil, and South Africa. So thank you very much for your attention.
Thanks a lot, Bärbel, and thank you also for keeping in time, or you were very quick, but with a lot of content and quite important content, because just the technical part, it's nice to have, but if there are no financials and nobody is willing to take the risk and to invest, we will not bring this type of systems on the ground. Now we are moving to the or more to the answer question. I received quite a lot of questions. I want to start with one question here. Maybe Christoph can answer it. There is one question. Unfortunately, the person who asked left the webinar already, but I think it's still an important question because it comes up all the time, is with the continuous falling price of PV panels, how does this affect also solar process heat? And here it's mentioned basically cooling, but I think this question comes up all the time. How is the competition with PV regarding industrial process heat? Maybe okay. Christoph can answer it, or Pedro.
Mm-hmm. Yeah, no, I can give an answer on this. I see not this big competition between solar thermal and PV on the process side, or the industrial process heat side, because there's always quite a huge demand on energy, on thermal energy, what also I showed with my first slide. There's really a need on thermal energy and not only on electricity. And if you, and there's always a limited space area where you can install your collectors, for example. And if you then have a look on the efficiency on both technologies, solar thermal is much efficient, much more efficient than PV. So this means for the same area, space area, you get out much more energy compared to PV. So if you don't need electricity, if you really need energy on certain temperature levels, and this can be covered by solar thermal, you will get much more energy out of your system, out of your solar thermal system. And so I see a big advantage here for solar thermal compared to PV installations.
Yeah, I think the range is typically from solar thermal collectors to PV, it's in the range of 2 to 2.5 times more area needed in order to get out the same amount of kilowatt hours. Mm-hmm. This brings me to the next question, which is also directed to you, Christoph. It was the question of what kind of thermal storage technology is usually used for the industrial process heat.
Yeah, so of course it depends which distribution system you have, but let's say normally there are pressure-less or pressurized storages, hot water storages, stratification storages, which are used in industry. So space is not, for these storages, is not really a crucial point. It's very often they're used to handle with large storages, especially in the beverage industry or in the food industry. So they're used to have heat sinks, heat sources, and to store this in 100 cubic meter, 200 cubic meter, 300 cubic meter storages. So these are the main technologies which are applied here.
If I may add a comment on that, considering capacity, not yet maybe competitiveness on the economic side, there is quite a few activities regarding research and development activities on phase change materials, especially for low temperature application. It's already rather common on residential applications, but more recently phase change materials for thermal storage systems in the medium temperature range. It's also upcoming topic, and we believe that we will start seeing products coming into the market based on phase change materials.
Thank you, Pedro, for adding this. Then I come to you anyhow, because the next question is was Luca Smoker asked if central receiver plants are no option for process heat, so especially for the high temperature industry, if they can be used at temperature above 400 degrees. So central receivers, are they taken into consideration?
Well, definitely central receiver technologies might be very interesting, especially when it comes to addressing the energy intensive sectors. There is actually a specific work package on the in-ship ECRIA. And again, I want to stress that ECRIA stands for European Coordinated Research and Innovation Agenda. So the objective is to coordinate research, to identify the most pressing research topics, and to coordinate research activities within Europe around the most pressing questions. And one of the questions is how to tackle high temperature processes. And for that, definitely we need point focus technologies, central receiver technologies are required, yet those are the ones which are maybe far from, from a commercial stage. When we consider the use of central receiver technologies for power production, for instance, the fact that we have the receiver on a tower, an elevated receiver, well, is not that much of a problem. Basically, we need to transport the heat transfer media up there. Sometimes we can even use air. When it comes to an industrial process, we have to transport raw materials, which is a bit more difficult. And of course, we will have different streams coming into this process. So to bring all of that into the top of a tower might be a bit more complicated, and it is certainly more complicated. One option would be to use beam down systems, but then of course introducing penalties on the optical side. So yes, there is some work undergoing, actually already some research along the last 10 to 15 years on how to design solar reactors. That's the first step. And then how to design an optical system which accommodates all of these specificities of transporting raw materials, transporting the final product, whether to have this reactor on a tower or on the surface, on the ground surface. So that would be my summarized answer to that question.
Thank you, Pedro. And there was several questions were on some of the participants missed that you mentioned high vacuum flat plate collectors.
Yes.
What do you think about these ones? There are some applications already and they were tested, but you did not mention it. And what are your views on these high vacuum flat plate collectors?
Definitely a very interesting approach. Actually missing the advantages on the optical side of flat plate collectors and the advantages on the thermal side of evacuated tubes. So we have evacuated flat plate collectors. That's a very interesting development. I haven't mentioned that and other technological concepts as, of course, trying to present a rather summarized overview of technologies and questions. I focus on the most prominent technologies, and those are definitely flat plate evacuated tubes, but on the low temperature, but also on the medium temperature side, there are alternative technological concepts. So the flat plate evacuated collector is one of these concepts, and a very interesting one, definitely. We have a rather extensive, we have a rather comprehensive database on available collectors developed in the scope of Task 49. Christoph Brunner referred to that database, and also there is a rather extensive and comprehensive documentation on solar collector technologies provided within subtask A documentation. So all of this documentation is publicly available on the publications part of Task 49 website.
This was an important hint. So for all participants, it might be interesting for you if you go to the IEA Solar Heating and Cooling website. Most of the tasks provide all the outcomes, so you can all download all these results. So I think it's worth to visit the website to find out what is available there. There's really quite a lot also from other previous tasks on this topic. The final question at the moment to you, Pedro, is there is one question from Jonathan Kaufmann. He was asking if you can use polysun to handle high temperature process design. And I would add, besides polysun, would you recommend as simulation program for interested companies? How should they approach this sector or this type of application?
Sure. Well, again, at this moment, I'm not fully aware of the latest developments on polysun. There is definitely the question on how to simulate phase change. So not all the available tools enable phase change simulation. So of course when we try to design a solar system which is going to provide steam both directly or indirectly through thermal oil, water heat exchanger, for instance, not all the simulation tools address phase change, or if they do, might be they do not address it in a very detailed way. And so we know that, for instance, in direct solar generation concepts, when we have a phase change within the collector itself, of course this changes quite a lot the heat transfer coefficients in the collector and affects the collector overall efficiency. So this is all well known, but of course there's research being done in these topics, and not all of those results have yet been translated into commercially available tools. There are some tools commercially available which can address higher temperature designs. I would mention, for instance, Greenius, some which is focused on CSP, but can also be used for higher temperature process heat designs, and Transys as the tools today available, which can maybe address these higher temperature applications. Then we have TSOL as well, addressing higher temperature applications. I'm not sure whether or not it abides to phase change, and Polyson, as I have already mentioned. I am not fully aware of whether or not addresses phase change. But there is also a publication on task 49, subtask A, where we have made a comparison of different tools and where you can find the features of such tools at least by 2016.
Thank you,
Just
Pedro.
one comment, Werner. Sorry, one comment. It was subtask C. If someone is looking for it, this report was on subtask C. This
yes,
comparison is
subtask,
different.
sorry. Yes, you're right.
Okay, so it's no problem, of course. If others want to comment and contribute, just let me know. There is anyhow a question to Bärbel and to Pedro on contracts and financing. There's one question from Roberto Roman, I think he's well known, and he was asking if you could give a little bit more information on the contracts, especially in Chile. You mentioned this big plant in Chile, which is at the moment the biggest one, and for the copper mining industry there are a lot of opportunities, Roberto mentions, in Chile, but the companies are reluctant to sign new contracts. So do you know a little bit more about these contracts and the background? Bärbel, maybe also Pedro?
Well, this is now a really funny information because Roman was a very important source of our information researching Chile, and if somebody can answer this question, it's himself because he knows very well what's going on in Chile. I think it's really the case that copper prices are reduced and the copper industry has a big heat need in our range, and they looked at the case study a lot, which was realized in Chile, but actually ever since only Mexico invested in a 2,000 square meter plant, which was also the success of this joint venture with Sunrain. So they actually succeeded to do implement a follow-up project, and they are contacting a lot of mines, but they are really reluctant in investing. And actually I have to give this question or this salutation back to Professor Roman, because he was the one who actually stressed that the system in Chile should be an ESCO. And I think all the players in Chile, they are absolutely convinced that this case study is such an excellent case study because it was implemented as an ESCO, because the mine itself would never have been able to run this solar system in such a difficult surrounding. So E.R. Nelson, when we interviewed him, the interview is on solarthermalworld.org, you know, he said that it took him 2 years to tackle the issue of water resources and cleaning frequencies and dust and sticky dust and everything you have to solve in such a desert-like situation, and they succeeded. They have an average annual yield which is 1,113 kilowatt hours per square meter over the last 3 years, which was almost about what they have simulated before, the ESCO. So I think that is really a good case study to look at, and anytime I will do more reports on that again, because it's really a success story. So nobody, I mean, everybody can use it in the industry. I think that it's a very well documented and good case study.
Okay, thank you. There's another question going a little bit in this direction. It's also for you, Bärbel. It's what are the main obstacles you think for the deployment? Is it also the low gas price, for instance, in Europe, and the competition of cogeneration waste heat? So what do you think is what are the main obstacles?
Yes, I think the main obstacle, I mean, we have asked this question the suppliers, and they should know, you know, and 41% of them answered that the low fossil energy fuel prices are the main barrier, you know, the high payback periods, and that what makes us create this vicious circle in such a dominant way, that these high fossil energy prices. The second important issue was that they stressed the lack of political will to address reheat, you know, and to have regulations which stipulate renewable heat in industry. And I think that there is a big time shift coming up now, because IRENA from these big REMAP studies really understood that industry is difficult to tackle, and we know this from the IEA. And if you repeat a message very often, you know, decision makers sort of brainstorm more about this issue. And I hope really, really that India will succeed on such a regulation, which is like a bit like a quote. I mean, we have very successful utility quotes worldwide, you know, in the US on electricity side. Why not have a renewable quote for industry in strong polluted areas in China or India? So I hope that they result in, or have sort of an outcome on this, because these were the main barriers besides financing that we heard from the suppliers.
Yeah, I think we had a quite good discussion, but we are more or less coming to the end. On the one hand, I think we saw now there are several obstacles. On the other hand, that's just my personal point of view. Nearly all countries worldwide, the governments signed now the COP21 agreement, which simply means we have to decarbonize our economies within 20 years. So no oil, no gas, no coal in a very short time period of just 20 years. So by 2000, in the next 20 years, we should really get rid of basically nearly all fossil fuels. And of course, the heat sector is more than 50% of the final energy demand worldwide, so it's a huge potential for solar. On the other hand, still quite some challenges on this. Before I really summarize very quick, I want to give a summary feedback to our colleagues from India. They mainly, it were not really questions, it was mainly comments. So there are several excellent developments going on in installations in India, it was mentioned. And the question was also why they were not presented. Of course, we cannot present all 500 installations worldwide. And they wanted to see IEA SHC coming to India. And I think that's just a question. India, unfortunately, at the moment is not member of the IEA Solar Heating and Cooling Program, but we would be we really look forward to getting more contact with India and to have a new participant in the IEA Solar Heating and Cooling Program. I think this would really cross-fertilize a lot if we get a good experience from India into the solar heating and cooling program. I think our discussion, we had something like, if I saw it right, we had something like 230 participants. I think we see the growing market in installation worldwide. It goes from small scale, so from maybe 50 to several hundred square meters, but also in the several megawatt scale systems. The big system in Chile was mentioned with nearly 30 megawatt thermal capacity, so it's going already quite big. We need all collector types, it was clearly stated, depending on the temperature level. And the crucial point in my point of view is really the combination of the knowledge of solar thermal experts and the experts of process engineering. And this is also shown at the end, that the opportunities for investors is, so there are a lot of opportunities, but it might be the case that you need really specialized companies who provide turnkey solutions, and if they provide heat supply contracts. So I guess the times are over where the solar companies can sell just collectors and leave it up to the others to run the system. It's time to have turnkey solutions and to sell heat in the same way like other utilities sell like electricity. And I think that's the way to go also for process heat. And with this, I want to thank all of you and want to hand over to Joanna again, because she will give us the final words on this webinar. Joanna?
Yes, thank you very much, Werner, and also for your very inspiring summary of this webinar. I definitely echo your sentiments, and I'd like to thank all our panelist speakers for sharing their knowledge and expertise with us today, and thank you to the Solar Academy for organizing this webinar. The next Solar Academy is already scheduled. Let me just get that slide up. And we hope that you tune into that one as well. That webinar will be on solar energy in urban planning and takes place on the 13th of September 2017. So mark your calendars. We will be sending out invitations to all of you. To contact the panelist speakers for further information about the details presented and discussed here today in this webinar, please see their own contact information in their presentations, which are all freely available for you to download from the ISIS website. The next ISIS webinar will take place next month, that's in early August, and will focus on solar cooking. We welcome you all to join. You'll find more information on our website. If you use social media, we encourage you to connect with us and to continue the discussion and stay tuned into the work of ISIS and the Solar Academy. Last but not least, I would like to thank our audience for joining us today. We look forward to welcoming you at another webinar. You may view the webinar recording in a couple of hours on the ISIS website and the Solar Academy website and YouTube channels. If you have comments or feedback, we welcome you to share this with us so that we can continue to improve the webinar series for you. Please participate in the survey or send your feedback to public.relations@isis.org. And that's it from me. We've finished on time. Thank you so much to the panelist speakers and to Werner for moderating this excellent webinar. Wishing you all a nice evening or morning, whatever time it is in your part of the world.
I also want to thank you once again, Joanna, for the excellent organization of these webinars and for the excellent cooperation between ISIS with us as an IEA Solar Heating and Cooling Program. So it's really I'm really looking forward to the next joint webinars. Thank you.
Thank you too.